Thus far in this class, we've looked at tests designed to assess the statistical significance of a difference between two means, either the mean of a population and the mean of a sample, or the means of two different samples. We can only use a t-test and a z-test when we have two means. If we have a study that involves more than two means, we need to use a different technique called analysis of variance, also known as ANOVA. An example of an ANOVA study might be an experiment where you have three different treatment groups. One group is a control, they don't get anything, and the second group maybe gets one level of a treatment or one type of treatment, and the second group gets, the third group rather, gets a different type of treatment, a different type of intervention. We might also have a survey where we have three different groups of respondents and a question that looks at, say, their income or their score on some kind of attitudinal question. For these kinds of studies, we need to use this ANOVA technique, which is what we're going to get into right now.
Let's start out by asking simply why we can't conduct multiple t-tests arrayed, say, like this. The reason is easy to articulate. Each comparison carries with it the probability of a type 1 error, that is, the probability of rejecting a null hypothesis that in fact is true. We typically set a probability of a type 1 error by setting an alpha level at, say, 0.05. The probability of making a type 1 error for each test would be 0.05, but the more tests we perform, the more the overall alpha level increases, and hence the probability of making a type 1 error when all the tests are taken together. We need to find a way of comparing the means from the three groups without using the means themselves in our calculations. Let's take a look at an example. Here are two separate scenarios. Let's say this is a study about age differences and attitudes towards capital punishment. A high score indicates more favorability towards capital punishment. A low score indicates less favorability. In scenario 1, the mean scores are fairly similar across our four age groups. It doesn't seem that there's much variation between the groups. Since the means are similar, this should be obvious. Note the row that shows the standard deviations. These are the standard deviations within each group. Now look at scenario 2. Here it appears that there are differences in the mean scores. Are they statistically significant? Look again at the standard deviations depicted in scenario 2. The standard deviations within the groups are all similar, but clearly there's a good deal of variation between the groups. This is what is at the heart of analysis of variance. So what do we do with these between group variances and these within group variances? Think back to the z-test and the t-test. We compared the observed differences in scores, the numerator of the t or z equation, with the expected differences in the scores, the denominator of the equation, by looking at the ratio of the one to the other. And you can see that depicted in this slide. We do the same thing here with analysis of variance. In any sample, we expect a certain amount of variance, a certain amount of variation. That variation, in the case of analysis of variance, is estimated with the within groups variance. The ratio shown here essentially compares the variance between the groups with the expected variance, which is estimated by the variance within the groups, and we produce something called an F ratio. We use that ratio to assess statistical significance. Let me just point out one other bit of terminology. The variance between the groups is called the mean square between groups, or MSB. The variance within the groups is called the mean square within, which is the MSW. You'll need to remember these terms as we'll use them later in calculating the actual values. Here's the formula for F. Like Z or T, F forms a distribution, and just as was the case with Z and T, we'll look up the critical values for f in a table, taking into account the degrees of freedom for the numerator and the degrees of freedom for the denominator. More on that in a bit, though. The next question is, how are we going to compute the MSB and MSW? Well, there are a couple of different approaches. All make use of this common sense formula, which states that the total variation in the study is made up of the variation within the groups plus the variation between or across the groups. Obviously, if we know any of these two things, we can compute the third by addition or subtraction. So how do we compute these? Pretty much exactly the way we compute any variance, which is to say that we divide a sum of squares by an adjusted sample size. The total variation is equal to the total sum of squares divided by the total number of respondents in all the groups minus 1. The within groups variance is just the total of the individual group variances, which are calculated by adding the sums of squares for each group and dividing each sum of squares by the number of cases in that corresponding group, again minus 1. In the formula as I've written out, there are just 3 groups, but we can have as many groups as we want. The between groups variance is the BSS divided by the total number of groups, and we denote that with K, minus 1. Just to be clear, I'm showing you these formulas here so that you understand how this all works. The actual calculations are straightforward. They are kind of tedious, but we'll get to those in the next slide. We can approach the formula on the previous slide by dealing with the numerators and denominators separately. For the numerators, we have TSS equals WSS plus BS. The denominators are the degrees of freedom associated with each sum of squares. Degrees of freedom total is the degrees of freedom associated with the total sum of squares. We don't really use this for anything. Some statistical programs will compute it for you. The degree of freedom within groups is the degree of freedom associated with the within group sum of squares. And the degrees of freedom between the groups is the degrees of freedom for the between group sum of squares. Again, K is the number of groups. These all come together here, where I've reproduced the formula for F and the formulas for the 2 component parts of F, the MSB and the MSW. We'll work out how to calculate everything we need in a minute. But first, let's talk briefly about the assumptions and limitations of analysis of variance. Okay, ANOVA requires interval or ratio dependent variables. That's similar to our T and Z tests. The sizes of the groups must be relatively equal to one another. They don't have to be exactly equal, but close. The within group variances have to be similar, and this maybe is obvious to you if you think about it a bit. If they weren't similar, the mean square within groups wouldn't be a good measure of the expected variance. And finally, ANOVA doesn't, and importantly, ANOVA does not tell you anything about which groups are different. To determine that, you need to run post-hoc tests. These tests function like t-tests, but are more conservative, so as to avoid the problem we started with, which was the probability of an increased probability of type 1 errors. All right, let's sum everything up. ANOVA compares the variation within categories with the variation between categories. That's the basis of this whole thing. The variation between categories is known as the mean square between. The variation within categories is known as the mean square within. If the variation between the categories is large relative to the variation within the categories, the value of f will be large, and we will reject the null hypothesis that the means of all 3 groups are equal. Okay, so now that you know some of the theory behind analysis of variance, it's time to get into solving some analysis of variance problems. I think that as you solve those problems, you should develop a better understanding about what is going on under the hood. So it's time to go on to the next video.